Radiocarbon dating then is a form of radiometric dating. Now, in the atmosphere there are three sorts of carbon. Carbon 12, which makes up 99% of all the carbon in the atmosphere, and there's carbon 13, which makes up about less than 1%, and finally a tiny amount, which is carbon 14, which is unstable and will decay radioactively. Okay. Now carbon 14 decays into nitrogen 14, which is a stable element. Now these three different types of carbon are known as isotopes, and they will all form or combine with oxygen to form carbon dioxide in the atmosphere. Some molecules of carbon dioxide will have carbon 12 in. For example, in this molecule of carbon dioxide, you can see we have two oxygens, and here is a carbon, but this will be carbon 12. A tiny minority of carbon dioxide molecules will have the carbon 14 element in it. So in this molecule of carbon dioxide we have the two oxygens again, combining. This time the carbon will be carbon 14, and this is the radioactive carbon that will decay over time. Plants will photosynthesize and take in carbon dioxide into their leaves. Most of it will be molecules of carbon dioxide with normal carbon 12 in it, but some, tiny amount, will be carbon dioxide molecules with the radioactive carbon in it. As soon as the carbon 14 gets into the plant, it will start to decay into nitrogen 14. But as the plant is alive, it will continue to photosynthesize and continue to take in carbon dioxide, and some of those molecules will be of carbon 14, and hence it will be replaced, keeping the carbon 14 content in the plant stable. So if we measure the amount of carbon 12 and carbon 14 in a living plant, it will look something like this. So over time there will be 100% carbon 12, this doesn't decay and keep being replaced, and there will also be 100%, just draw it underneath this line, but it's 100% carbon 14, because that's being constantly replaced as well. However, if our plant or tree should die, it can now no longer photosynthesize, it can't take in any carbon dioxide from the atmosphere, so it's not going to replenish the radioactive carbon 14. So in the plant now, the carbon 14 will decay to form nitrogen 14. Over time then, instead of remaining constant in a living plant, the carbon 14 will slowly decline over time, getting smaller and smaller and smaller over time. Now this decay and reduction in carbon 14 can give the age of the organism. For example, after a certain amount of time, half of the original unstable carbon 14 atoms will have decayed. And if we draw a line across to this and down, that will equal 5,730 years, because that's the half-life of carbon 14. It takes 5,730 years for approximately half the original unstable carbon 14 atoms to decay into nitrogen 14. if we half that again, so we're now down to 25% of the original carbon-14, and draw our line across, we have add another 5,730 years, so that is now 11,460 years, and that equates to 2 half-lives. We can go down again here to 12.5%, so that will be a line drawn across here and down. We can add another 5,730 years, which comes to 17,190. So it takes 17,190 years for the carbon-14 to decrease by half and then half again. If you notice at the same time, I've not rubbed out the blue line here, but the carbon-12 remains the same. And scientists can measure the ratio between the amount of carbon-14 in an organism that's dead and the amount of carbon-12 in there, and give a date in thousands of years. Now, this technique can only work in organisms that have carbon in them, so it needs plenty of carbon, and it can only be for quite recent organisms up to 60,000 years, because at about that time there's so little down around here, so little carbon-14 that it's very hard to measure and the readings aren't very accurate.